So we are online.
So welcome everybody. Thank you for joining us today for the mathematical physics seminar. We have Giorgi Gubbiotti from Università di Milano, which we talk about coalgebra symmetry and discrete time integrable. Okay.
Thank you. So thank you for the invitation. The complete title of the talk can be Coalgebra Symmetry and Discrete Time Integrable Systems with this subtitle, which is about the SL2R case, because, well, first because it's in some sense it's the simplest one you can think of, and second because it's the only one we have sort of complete result at the moment, because that's from we introduced this notion of coalgebra symmetry in discrete time actually in 2021, but the paper was published only very recently. And funny enough, this case, which is actually a sort of application of the general method, got published first because the journal was quicker than one journal was quicker than the other. So I will not assume you know anything about the coalgebra symmetry ideas, so I will start from the very beginning, and just in the end I might just show some resuming tables of our results, but what I would like to convey first are the ideas of coalgebra symmetry. So what it means for a continuous time and a discrete time to have coalgebra symmetry, and what it does imply. First, let us go to the very beginning. So what is the aim of the method of coalgebra symmetry? The aim is to produce integrable systems Hamiltonian in the continuous case, or symplectic maps in the discrete case. Starting from in arbitrary dimension, in arbitrary degrees of freedom. I prefer the term degrees of freedom because it's the dimension will simply be just twice the number of degrees of freedom when we are in the symplectic case. In arbitrary and degrees of freedom from 1 degrees of freedom system. And so the idea is something quite powerful, because it means you have something which is 1 degrees of freedom, which is sort of rather trivially integrable, because of course anything in dimension in 1 degrees of freedom conserves energy, so it's already integrable, and use it to produce something in n degrees of freedom which preserves integrability. Actually, it is more than integrable. It will be something that is actually always super integrable. So it's even more than just integrable. This idea of using the coalgebra of algebras and this kind of structure and integrability came much later, the introduction of this concept, because the concept of algebra is even older. But like all the stuff about coalgebra and these kind of things, it mostly comes from the theory of quantum groups. So it's the work of Drinfeld and other people. But it was developed mostly by Ballesteros and Agnisco. And the very first paper where the seminal idea of this is a paper by Angel Ballesteros, Coalgebra, and Agnisco. The Czech Journal of Physics, I never, but I want to be precise. Yes, it's Czechoslovakian Journal of Physics. Of 1996. So much later, the introduction of Coalgebra. Let us proceed with for the end of this talk, I will not speak about general coalgebras. I will stick to Poisson coalgebras, which are the ones we need to produce integrable systems. So we'll have my coalgebra is a pair where A and delta, where A is a Poisson algebra, and delta is the coproduct. So the coproduct is first of all, we are in a Poisson algebra, so it needs to be a Poisson homomorphism. Simply means that preserves the Poisson bracket. That's compatible with the Poisson bracket. And but the most important property is it is co-associative. So it means that delta tensor, the identity map, composed again with delta, is equal to the identity map tensor delta composed with delta. Or if you prefer, in terms of commutative diagrams, this means that we have a diagram of this kind. We start from, oh sorry, first I did not tell you that it goes from A to A tensor A with itself. So we have our algebra, Poisson algebra A. We act with delta, and we end up in A times A. And then we act with delta tensor the identity. So on the first factor, I act with delta, and the second one, I just act with identity. And I end up in the thrice tensor product. Or the other way around, I first act with delta, then I again end up in the tensor product with itself, but this time I act with the identity on the first factor and with the coproduct in the second factor. And this condition means that whatever path I choose, I end up in the same manner. Yes?
Isn't the first step of the path the same for off-road?
Yes.
So you could actually go just one line?
Yeah.
Yeah. Right.
Just that, yes, you.
But it's not true that if I remove completely the left factor, this is still a commutative diagram.
Yeah, because the idea is that the coproduct more or less is an operation that allows you to write in a simple way the basis in the tensor product. So you have an algebra, its tensor product itself, and this one is a nice and simple way to write down elements within this tensor product, starting from the elements of this tensor product.
This is surjective.
Sorry?
It's not a surjective map, so it gives you part of the basis. Not all.
Yeah. And okay, so the idea. So why is this important? Well, if we want to consider the case which is usually most studied, which is the case of the algebras, there is a so-called primitive coproduct, which is valid for all the algebras, which is why it is sort of simple. So you start from the algebra. Then, of course, you should be considering its universal enveloping algebra, because you want to take you want to promote it to Poisson the algebra. So you actually want something more. And then in this case, there is always the primitive coproduct, which is so if so assume my G is the span of some elements. I call it J1 up to Jm. Then the primitive coproduct is just defined on the base element as delta of Ji is equal to Ji tensor unity plus unity tensor Ji, and on unity simply act as unity tensor unit. So this is and this is always valid for all the other. So this is why
it's not valid for
sorry?
It's not valid for example.
It is.
On H. The carton. So you okay?
Yeah, it's valid as far as I do. It's valid. To check. So so let us go to the next step is to iterate the coproduct. So we want to define either coproducts which are same properties, but we will end up in some tensor product of the algebra times itself m times. And this is why we will go to eigendimension, to go from one dimension to n dimension, because this is the key step. So we want to define actually we have two. We will have a left and a right mth coproduct, which go from my algebra A to A tensor with itself m times, and again tensor with its n times, which are defined recursively. So the delta of L M, so the left product is delta for M equal to 2, or identity times identity times identity times delta 2. This is just M minus 2 times the tensor product of the identity, composed with delta minus 1, or we have the right coproduct, which, well, not surprisingly, for M equal to 2, just coincide. But this time, I have it delta 2 on this side, then tensor M minus 1 times with the identity, and yes, and then composed with M minus 2. So we have a sort of lattice where we iterate this sort of property where you just extend it. So you go A times 2, A times 3, and so on and so forth. You can extend the number of times you like. And so this is, and if you fix a number n,
Sorry, what is delta 1?
delta 1, of course, there is no, it's just for n greater than 2.
Yeah, because in your formula you have a delta 1 at some. If m equal 3, I have it's 0. Okay.
3,
If m equal 3,
I have 2.
no, m minus 1, it's. Ah, okay.
3 is
Okay, sorry. Okay.
Am I correct? I think
No, it's okay.
so sorry, yes. For sure, this is m greater than 2. This is m greater than 2.
Okay.
Not possible. And, well, of course, you can say it equal, but, well, of course, equal is just the product we just defined. This one should, if you pick up 3, that one should go back to M2, I think. So it should be delta 2, which is just delta.
Okay.
Does this sound convincing?
Yeah,
okay.
Sorry.
Okay, no worries.
I miscomputed.
No worries. So you end up with some fixed delta, there's a fixed n, sorry. Then if you fix an n, then you have the nth left coproduct action on the j's and the nth right coproduct acting on the j's is the same. But this is not true for the lower order one, because in general, from the formula, what you can see that if you think of tensor product as adding sides to your to your space, then the left one will be depending on the sides from 1 to m, while the right one will be depending on the sides from n minus m plus 1 up to n. So it's like they are separate. And
sorry, you fix n.
Yes.
What is not?
If you fix n, your last coproduct, your last left coproduct will be the same.
What is? Give me an inequality. Give me
something that's not equal.
Yeah.
We don't understand the case of that.
Okay. Yeah, so if I fix n, then this one over this sides will be different from the one you encounter from the other side.
Okay, so it's only the entire chain.
Exactly. The entire chain. You know, important is fix n and can fix the entire chain.
I can start at any point.
Yes. But the ones in the middle will be different.
No, because of associativity. For associativity.
No, they will not be the same. I can show you one. I will go to the
example.
Yeah, the example it's simpler if you go to SL2 maybe that's the simplest one. So we'll so for SL2. Oops. So SL2 are pre-generator plus oops J minus and J3 and let me check if I written down or not. Okay. Then I have the maybe this is not very good. It's fun first, and then I have the commutation relation. J2 J1 is J3. J2 J3 is minus J1, and J3 J1 is 2. So let this one as the Casimir.
J2 and J1, do you mean J plus minus?
Yes, sorry, of course. Why am I considering this one? Oh, sorry. So let me check because since there is always the ambiguity if you want to use SL2 or the SU11, and I know it's mistaken. So, okay, now let's do this with this representation because otherwise the Casimir is not there. J3, J plus, J plus, and J3, J minus, minus 2, J minus. So this one has the Casimir, which is J plus, J minus, J3 squared. This is the Casimir of this algebra. And then, so we have the primitive coproduct. And then what we have is that one can say, what if we take the coproduct of the Casimir? Does this give something trivial or this gives something new? And hopefully this gives something new, because if you expand this, you have this one is J, by the properties of the coproduct, you have this one is delta of J plus, delta of J minus, minus delta of J3 squared, which is, if you do all the computations, you end up with T times identity plus 1 times C, tensor C, plus some new stuff, which is J plus tensor J minus, plus J minus tensor J plus, minus twice J3 tensor J3. So how much time do I have left? Oh, but there's plenty of time. Okay. So, so one would expect this gives nothing new, but if it gave nothing new, then you will only end up with this part here, which will be trivial. But in fact, it is not, because there is this additional terms here. And so the point is that now what we need to build the Hamiltonian system, we need the representation of the abstract algebras, of the abstract Poisson algebras, as Poisson algebras on some symplectic variety. So then the next key ingredient comes, which is just the representation D, which is something from the algebra within some symplectic variety M. We call it actually a realization. I don't know if this notion is sort of standard. We simply call it like this, and of course we have to impose that if I have some generator, this one should preserve the Poisson bracket. So del d of ji, d of jj. This one now is the Poisson bracket on the variety, must be equal to d of the Poisson bracket, and this one is the Poisson bracket on the Poisson algebra. Of course, in general, I will not go into the full variety. It's enough to go in some open subspace or some symplectic variety. So what is, so the question is, what is the representation of SL2R as a symplectic representation? Well, this is this one. So G of the plus. So I'm taking take C1 and phi1 as in an open subset of R2 as conjugate variables, so with the standard canonical bracket. And this one is my representation. It's phi1 squared plus B1 over C1 squared. Delta of J minus is B1 squared. And delta of J3 is the product of K1 and Q1. So in just this one would be a generalized coordinate, this one would be a generalized go like this. And then something bad happens if you check what happens to the Casimir. Sorry? Just a constant. It can be in principle any number, any real number. Actually, it's important because this one will come out too. So of course you can check that with respect to the canonical Poisson bracket, these three functions actually satisfy the commutation relations I gave you above. So this is what we call the realization of the.
So I should think of C1 and I1 and
Yes, yes, it's the canonical momentum. Yeah, so the question of course is, so that is down just for clarity. It's psi 1 pi 1 is equal to this is so this is just the standard canonical form on a. So if you want, it's just my simplicity m of 1 because dimension is degrees of freedom is half of the dimension is just r squared with the canonical Poisson form, and the elements, the points are labeled by C1 and phi 1. So if I try to compute the Casimir, then something seemingly bad happens, because if I try to compute the Casimir with this definition, it's easy to see that you simply get the constant 1. But this is not too surprising, because of course, if you think of it as a Hamiltonian system, you will not have any other non-trivial constant of motion besides the Hamiltonian. So it is even though it's seemingly bad, this is actually correct, because it simply means that we don't have any other non-trivial additional quantity. But let's try to do it with the second, with the second. So now what we do the tensor product of the representation to build the tensor product of the to act on the tensor product of the. So maybe here the things of sides gets a little bit more clear, because we simply think of this associated to a side 1 and the second representation assigned to a side 2. So what we have, for instance, of J plus is just phi 1 squared plus phi 2 squared plus b1 squared over x1 squared plus b2 over c2 squared, and so on and so forth. So the tensor d of j minus is c1 squared plus c2 squared, and d times, let me go to next line. Of J3 is just C1 by 1 plus phi 2 by 2. And then the magic happens. Then the magic happens, because now this one I can think of it as defined on now my variety, now my manifold is M of 2, which will be in, well, an open subset, because I have some singularities. Therefore, with omega, so it's two-dimensional. But so if I want an integrable system, of course, the only the Hamiltonian is not enough. I need to have at least another invariant. And if I take the tensor product of the representation of the Casimir, and I develop my computations, what I end up is this non-trivial function, so no longer a constant. So what we see is that if we take, so I guess there is this, of course, this one. This one. Here they are coupled. So then you have 1, 2, 2, 1. So what do I see is that if I take an Hamiltonian system, dimension 2, where my Hamiltonian function is a function of, well, let's call it like this, d tensor square of J1, d tensor square of J minus, d tensor square of J3, that is simply function of the things I wrote before, so it's, well, I won't write it down because it's just too long, but I guess you understood. Then this one is an integrable system, because what is possible to check, this one was a Casimir of my algebra. I can possible to prove this, that if you do the, sorry, let me see. So the proof is that if you have a Casimir of your original algebra, then the coproduct of C is a Casimir of A tensor itself. And this, and in particular, it commutes with the generator. Commuting with the generators, it means that if I take an Hamiltonian, which is made of my generators of my coalgebra, of my representation, then this one will be an invariant. So I will have that. So let's call this one C2. So I will have that the Poisson bracket of H2 with C2 is 0. So it means that the Hamiltonian flow of H2 is infinite.
Sorry, but how do you define H2? Is there any H2 you
It's
can
any
use?
function, yes,
Any
it's
function.
any function. If you want it to be, say, for instance, a natural Hamiltonian, you just remove the dependence on J3 and take linear dependence on J2. This will give you a natural Hamiltonian. And this is just, so this will be sort of a system with some centripetal barriers, because this linearity is 1 over something, are just centripetal barriers with radial potential. Okay, so then the next part, of course, is to generalize this kind of uh, of um, idea. And now we'll go back to this one because the formula which is rather bad written here. Oh. So now we can go to n dimension. Let's stick to the SL2 case because the general construction is more or less the same. So, okay, we can more or less, at least in our identify the representation with the algebra itself because they have just the same, so that I can drop the capital D's around, which are just very heavy to carry. And then if I go to an n-dimensional representation for the J of n, obtained in the same way as before, so just by tensoring the various elements, I obtain a representation of this form. I have sum from I up to n of pi k squared plus bk k squared. Then a representation of j minus n is just the radial element, and j3 is the sum of the products of the two coordinates. And now it becomes, okay, now it becomes important, the fact that we have left and right Casimirs, because now we can actually write down all the Casimirs up to n, and you can see explicitly why they will be different up to some point, but they will be equal only the last one, because if I repeat the computation I just did before, first I can do it abstractly, then I can just put it into the specific realization. I will end up with the following Casimirs. There's Cm I, which is the sum from I from 1 up to j and m of aij squared plus bi times j over ci squared plus bj, just invert the index here, plus the constants, and where Lij's are not in that components of angular momentum like function. So it's just like Ci pi j minus pi I pi j. And then there is the Cm lower, which is equal to same sum, again a sum, but this time from n minus m plus 1 less or equal than I less than j from up to, sorry, this time up to capital N, exactly of the same object as above, plus sum from j from n minus n plus 1 up to capital N, again of bj. And so abstractly, These come from Casimir's in the M product of the algebra with itself, and this is just the realization. And you can see if you put n equals to here and capital N equals to here, that the last two are the same. Because of course I let my m vary from 2 up to n, but what you can verify is that they depend on different sides. So they are never equal except the very last one. But of course, these are not all functional independent. I'm not claiming this because that would be clearly false. I'm just saying that these are not the same. And now the integrability. Now you have the Hamiltonian. Allow me just to change the index. Is here I have n. I just take the n representation, which is what I have written above. And then I have integrability. I have Liouville integrability. So a set of commuting first integrals, all commuting within themselves in two ways. First, I have a set which I call L, which is Hn, and all the upper Casimir's up to Cn. So these are functional independent commuting first integrals for the Hamiltonian for generic values, completely generic. So you can just take an arbitrary.
So the theorem is that Cm commutes with Cm plus 1, which
Yes.
is the theorem.
Yes, exactly. Sorry?
Is it obvious?
No, it's not that obvious. It's you have to go to the paper of the paper of by yourself. But it's not too difficult, but it's not completely trivial.
Sorry, you are in different spaces. The Casimir or U times identity. C2 is in.
No, of course you what you think is that you embed every tensor product within the next tensor product.
Okay, just
so
with
that you can always think that you are in the last one.
Okay.
Yes, that's a very good observation. It was not that one I think was sort of put under the carpet in the first paper. I think it was discussed a little bit better in a work of Fabio Musso, which is much later than the first paper of Ballesteros and Renisco. It is in the late 2000s. So yeah, that's a very good observation. I tried to put it under the carpet, but you busted me. And then also Earth, which is the very same. Oh, sorry. C2 up to Cn. So that the question is for every n greater than 2, this is a set of function independent commuting invariants. And so actually it gives a little bit more, because if you do some additional computations, what you end up is that you can prove that the set, which is given by actually L union R, noting that just the last two are just the same, is made of function independent invariants. So it means that I have 2n minus 2 function independent invariants. And in the theory of superintegrable system, this is what you call a quasi-maximal superintegrable system, because if it were n minus 1, it would be maximally superintegrable. Maximally superintegral are very special because they have the orbits which lie on, all closed orbits lie on, so all finite orbits will lie on closed curves. That's theorem of Hiroshi. And these one are just the slight generalization. So this one, I will just say this is quasi maximally superintegrable system. And so this is the construction for the continuous part. For the discrete part, I don't think I have enough time to explain it in the details. So maybe I can switch to the
Yes.
presentation. Thanks. Just to
You
show
can take
the,
10 minutes.
okay. Well, that will take some time just to discuss the results. I think I have to put a password.
Yes, I'll tell you. Well, I'll write it 1 second.
Okay.
I have a question.
Sure.
So the first case was Toda, wasn't it? Or set2, the Hamiltonian, with Casimir.
So the first case being n is equal to 1.
This case I want to call it, well, so you say the Toda, for the first Toda, I don't know if it's equivalent, to be honest. I will call it maybe that the very first might be something more like, I will call it like a more discrete internet system. I don't know if you know this denomination. It's, that one, okay, of course I erase it, but like the dimension 2 superintegrable with this kind of barriers is something that was discovered actually in the quantum case by the people in Dubna at the end of the 70s or the 60s. I think it's 67, the first 65, the first work. But I don't know if well, there is of course a relationship of todas with the algebras, but I don't know exactly about the connection with this construction. Because I'm not even sure that all the todas are superintegrable, to be honest.
I think he's just asking before you start.
Yeah. Yeah, okay. That might be, but it might be just for lower dimension. Because if you go higher dimension, this one will always give you something which is superintegrable.
Oh,
so
for any, you mean by dimension, what do you mean?
The degrees of freedom, number of degrees of freedom. So
yeah,
it's
we're just talking about the basis.
n equals 1. Equals 1. Maybe then it might be equivalent to todas.
You can think of this as a sort of construction that uses Toda to get these higher.
Yeah, exactly. Exactly. Yeah. Yeah. Maybe from my background, I won't have started with Toda. I will start with this more discrete internet, but that's exactly the idea. So actually, so the point that apparently what was missing from the literature was an analogous definition for discrete time systems. In discrete time systems, we have an additional problem that we cannot define an Hamiltonian with the same properties of the continuous Hamiltonian, because you can think a discrete time system, autonomous discrete time system, as a sort of as a canonical transformation between a symplectic variety to itself, and then it will be like a map that goes from the symplectic manifold to itself, pushing the state of my canonical variable to the time t to a time t plus some h finite, and you will iterate the map. But then, of course, You can see this as a canonical transformation of point of Mn, but canonical transformations have generating functions, which are their equivalent to the Hamiltonian, which unfortunately are not conserved quantity. So you cannot exactly do the very same construction for discrete time systems that is done for a continuous time system if you want to build something integrable out of the Coalgebra construction. So what we came up with is a slightly different construction, which instead involves a different approach. Instead of using the Hamiltonian, we use the evolution of the generators, and we claim that if so, we have a Poisson coalgebra again with some generators. We take our representations in n degrees of freedom, and then what we check is that this representation of the Poisson coalgebra needs to be closed within the evolution. So that if I evolve my map and I evaluate it on the generators, which are now real functions because they are we already using the representation, and we check we still are inside. We check that it is a Poisson map, and we check if it preserves the Casimirs. If we have these three conditions, then we can exactly claim the same general result as in the case of the continuum case, so that we have the Poisson or the symplectic map, which is endowed with this coalgebra symmetry, naturally admits some invariant. This is just the number. Well, of course, now is not important. It's just that it admits some invariant that might be enough to prove integrability. That will depend on the representation, and that will depend on the choice you make. Then we proved that this was actually possible to be used to isolate some new integrable system, some old and new discrete integrable system in the first paper, the one that got published second on Journal of Physics Day. And then what we turned out on is the problem of classifying all discrete system that allows the coalgebra symmetry with respect to some given Poisson algebra. We started, of course, with SL2 because it's the simplest one. We take the realization I showed you earlier, which is exactly this one. It's written down here. And then what we proved is that the systems which have a very specific form in the sense that they are we started from a quite generic class of system, just enough to allow to recover all known cases. That was our initial guess. We started from the Lagrangian viewpoint because it was easier to work with in the discrete case. And doing so, we ended up fixing the form of the generic Lagrangian admitting this whose associated system admit the coalgebra symmetry. But then this is not enough because we are missing the Hamiltonian. So what we turn to is we explicitly search for an additional polynomial first integral, and we found that there exists one for invariants of degree 1, degree 2, and degree 3. And what we end up more or less is this, what we were fixing is the form of the potential, the discrete potential B. And what we end up is a class of potential. I think there is an error in the first one, which should be squared, which gives some new and some old and new systems. I think that our nicest finding is that to this potential, which is wrong because it should be squared, alpha 1 squared over 2, in standard form, that means that these bk are equal to 0. We simply get a very simple system, which is just an discrete isotropic harmonic oscillator. But if these b's are different from 0, then we get a discrete version of the n-dimensional Zmorodisky internet system, which was something that was remarkably absent from the literature. And maybe I'll stop here and wait for some questions. And I just hope to try to convince you that this method is very good to produce integrable system, and there is actually much more thing to do because we just started exploring the possibilities of the discrete of this discrete definition of Coalgebra symmetry. Thank you so much.
Any further questions for Giorgio?
So everything you produce is super integrable.
Yes.
Right. So can you think of some way of making it less?
You can usually the fact is that you should. It seems to be that there are some modifications, very simple ones that you can do to make the systems less super integrable. And we are actually also thinking a little bit about it. So, for instance, for the Zmorodisky internet, what we did is we obtained the form of the system just by noticing that you can add you can change some parameters slightly. We ended up with discretization of another system, which is say someone call it the Evans system, which is just the Zmorodisky system, but with different frequencies. But there is one problem that still puzzles us a little bit, is that this system is known to have some super integrable, not maximally super integrable subcases, which we are not able to see in the discrete setting. So we obtain a sort of integrable, but not super integrable when needed discretization, which is not completely satisfying, at least for me. Maybe Danilo cares less because he's more into this kind. I am also working mostly in discrete systems, so it was a little bit unsatisfying to find some systems that do not preserve all properties of the continuum ones. But of course, yeah, playing with parameters will produce systems which are less super integrable. Another thing you can do is like instead of we did this construction with SL2 very tight for one. In the literature, there were some construction where like you use like some sort of intertwined algebras, so that you can change your parameters within the algebra, because the construction forces you to use the same parameters in some parts of the algebra. But then it becomes what has become more difficult is to prove Liouville integrability, because if you play too much with parameters, you might end up not having the sufficient number of invariants in the final algebra. So that's the tricky part. But then of course you can still produce some candidates.
One. So I don't know any of these discrete systems which are here, apart from autonomous discrete one, which rings a bell. But so I know that for other Pauli equations, general discrete versions of them are related to background transformation that you can have for the continuous one. But discrete but P1 has no parameters.
Yeah.
Right. So how the discrete one comes.
The-
I mean, if there is a relation with the continuous one apart from
well,
the continuous
because
limit.
actually the discrete P1 actually, if I am correct, comes out from a Beckmann transformation of Pauli. I'm correct,
be possible.
but I am. But actually, that one actually is a tricky system because it is very similar to the autonomous discrete Pauli one. But we are not able to find a continuum limit. So we don't really know if it is a discrete version of some Pauli-like continuous system. So that's so we don't know exactly. So that's an open question.
I have a question. When you introduce the generators of SL2, you said G2, G1 is Q, G3. When you take the representation with D, what happened to the?
No, what? Sorry.
When you take the D application,
Yes.
what happens to this commutation relation?
It's preserved, of course, because it has to be preserved. It's of course with respect to the canonical commutation.
Then let's thank speaker again. And if someone wants to come for lunch with us, we are going in